Hello, and welcome to our second module on earthquakes. And so for this lecture, we're going to focus on the hazards. And so in earthquake 1, we kind of focused on understanding earthquakes, why they shake the ground, how we locate them, how we determine how much energy is released for them and the magnitude. So we just want to run through some of the hazards, and some obvious or more obvious than others, but some you might not think of when it comes to earthquakes. So we're going to kind of run through those. And so when we first start, we want to think of some factors that impact the amount of damage that occurs. And so, yes, it's true that you can say a larger magnitude earthquake should potentially cause more damage. But we could compare a large magnitude like a magnitude 8 with a magnitude 6, and potentially there could be more impact on society in the smaller magnitude. And that is because that is not the only factor controlling damage. And so as we look at the list of things here on the slide, certainly how far away you are, so your location. But really, when we think about the impact on society, it's really about the people. And so we could argue that a very large magnitude earthquake that occurs in the middle of nowhere really doesn't have a big impact on society because no people are involved, no structures are involved. And so the more people we put in an area that is susceptible to earthquakes, then the more damage can occur. And so how many people there are in the location plays a really big role, and this building design and construction plays a really big role. So you might notice that in the news sometimes there'll be an earthquake, and sometimes they're not very large, a 5 or 6, but depending on where it happens, and a lot of times that's related to the ability to design and construct earthquake-resistant buildings. In countries that are poorer economically, they might not have the finances to do that, and so when there's an earthquake, even if it's not super large, the structures fail. And of course, people are in the structures, and this is where we get a high death toll. And so usually the argument isn't that earthquakes kill people, it's the buildings that kill people because of course they collapse and we are, as humans, inside those buildings. And so construction and design plays a big role. We talked about the size, but also the duration. And so there is a small little video clip on the main page of the module this week that talks about how you can get an earthquake that lasts for a long period of time. And so at these locations where we have especially a subduction happening, there's an interface there that's really big. And so a slippage on part of it can initiate slippage along the whole interface and cause multiple energy releases, right? And that can make the earthquake seem like it's lasting a lot longer. So some buildings just can't withstand that. They can handle 30 seconds, but can they handle a minute or 2 minutes or things like that? Geology or ground material, right? What did you build your structures on? And so different rock types, different materials behave differently when the energy is moving through them. And so really interconnected hard rock like igneous rocks like granites and things like that, when the energy moves through, they're so kind of compact that it's efficient. It goes through really quickly. Where looser material, certainly sediments, stuff that hasn't turned into a rock yet, those react worse, I guess. They amplify some of the energy because the pieces actually bounce into each other because they're not glued together or they're not crystalline growth together. So they actually shake and then they impact the piece next to it, which then shakes. And so that amplifies the ground shaking and can cause some issues for sure. Time of day or week, you don't think of that, but certainly we're relating this to where are the people. And so if they're all kind of gathered in structures, then, that's a problem. Or if they're all on the freeway at rush hour and the freeways collapse, that's a problem. So certainly that can play a role. And distance, we talked about distance from focus. Remember, the focus is inside the earth. So shallower earthquakes, the energy gets to the surface without dissipating very much. Deeper earthquakes don't really have as much impact. And of course, on the surface, if you're close or far away, that plays a role. So these are kind of the major ones you want to consider when we talk about, what other factors besides just a big earthquake can cause more damage, right? So keep that in mind. Now, certainly when we talk about earthquakes, we think about the ground rupturing or breaking. And that is true. Certainly during some earthquakes, we can see a failure all the way to the surface. That's not always true, but certainly if there's structures or anything above the, surface here, if there was a road or a building here and there was a big rupture, yes, that would cause some problems. And so the idea that you would be right on a fault as it uplifted is pretty rare. But of course it does happen, and we know that we build around or near faults that are exposed at the surface, so it's something to be aware of. If we look at this, we can relate this back to our previous lecture when we talked about, well, what type of fault is this? So they've drawn this diagram here that illustrates what you're seeing here in this live photo. But this slant, this angle here, is representative of the fault plane. So it's dipping, tilted, kind of like this on an angle. And this left side here went up, this right side went down. Remember, if we could pretend that there's a plane that goes into the earth here, we put our pen or our finger or whatever, our cursor on the fault plane and go straight up, this block here is the hanging wall. And it went down, and so that's a normal thing to do, down the slide or hanging a wall down. So this is a normal fault, and we could argue that there's probably some tension here, right, pulling the rocks apart. And this is why we see this type of rupture at this location, right? So, but of course, the destructive effect is having, ground rupturing beneath your feet or disrupting a structure that's built along or near this ground rupture. All right. Some other images of ground ruptures that we can see, sometimes they're just little cracks like this because the soil is not strong enough and we see a crack. We could see some movement like this. Now, of course, in this case, it's hard to know where the fault plane is. Is this the fault plane, or is it just because the fault plane didn't quite make it to the surface and this material that's on top, the soil, kind of broke in this fashion? So it would be difficult to ID this type of fault just from this image, because we need kind of a tilted fault plane to kind of identify it, at least easily. We would have to use some other information for that. But certainly this one, we could see that there is a more side-to-side motion. And so we know that if we have some offset on the surface like this, a horizontal offset, we would argue this would be a strike slip fault, right? So shearing is happening in this image to the right. But these are other ways that the ground can deform. You're not going to see, like in the movies, where it opens up this gaping hole and everybody falls inside. That's not how the faults work, right? So, and like I said, you don't always get a rupture or a disruption near the surface. But here's some examples of that. Other destructive issues we run into is something called liquefaction. And so what this is it happens not everywhere where there's earthquakes. Usually in coastal areas, and of course we know there's areas that are susceptible to earthquakes that are near the coast, California being one of them. Reason that's true is because, now we haven't talked much about this, but look, when we get rain that falls onto the surface of the earth, it percolates down through the material and it kind of settles in the open spaces between pieces and things like that. And we end up with what's called a water table. This is where we can drill into the ground and pull out water like from a well. In coastal communities, the water table, where the water is at depth, like how deep you have to dig to get to it, is pretty near the surface. And so in this diagram here, we see that, the sand grains or mud grains or pieces of rock, when it rains, the water is percolating through and is actually being stored in these open spaces here. What happens when we get ground shaking is the pieces bounce back and forth, because remember, these aren't rocks here, these are sediment pieces. And so as they bounce together, they squish the water, and the water actually gets kind of pushed upward into the overlying dry material, causing it to become saturated, and then we get this kind of liquefying of the land surface. So it seems dry at the time before an earthquake, and then what we get is this temporary liquefying of the soil above, and then things either sink, and like this example here, we have this building. There used to be a door that extends down here. It just kind of sunk down into the ground, or it flows a little bit, like in this image here, where it kind of, moving around. We even have examples where, the structures themselves don't crack or break because they're built fairly strong, but the foundations are on soil that has liquefied and they kind of tilt or fall over, something like that. And so an example, I have this on the main page too, so you could take a look at that, but I'm going to try and show you this here really fast. And so this is, let me go to that maybe. Okay. So really fast. So this is a demo. All right. And so what this gentleman here is going to show you is how we have water and sediment that exists. So he's dumping water first and then the sediment. But if I jump ahead really fast here, he's going to take that water. And once he puts all this material in, you could see. Okay, so what you could see hopefully is, sorry about that weird cut, but that there is some water in the subsurface here, okay? And so there's dry material at the top here, so this is what we would see if we were living on the surface. Hey, there's water at depth we could drill and get, but it's all stored in the open spaces here. But as we move through and actually shake the ground, so he's going to put a couple little structures there, and the skateboard is going to be the earthquake, right? Shake it. And what you'll see when the shaking occurs is that these material, the little grains, are actually bouncing to each other, and the water moves to the surface. And now everything's saturated, and we get this liquefaction where temporarily the surface turns to a liquid, and of course any structures that exist there are, knocked over, or they have issues with things like that, right? And so, all right, let's see if I can go back to what I was doing here. So the next thing that's how liquefaction works. And if I just confuse the crap out of you by moving stuff in and out of the screen, there is that little link on the main page about liquefaction that you can take a quick look at to understand that a little better. Okay, another hazard that we want to talk about is tsunamis. Now, we do have a module just on tsunamis because it has such a large impact on society when they occur. But what a tsunami is it's a wave that is generated from displacing a large amount or volume of water. Usually we associate this with earthquakes. Now, we can get it from other things, right? So we can get it from a landslide, a material that splashes into the ocean. Certainly you can get it from a blast underneath the ocean. You can get it from an object slamming into the ocean, like a meteorite or something like that. But because we're talking about earthquakes, in this module, we'll argue that the tsunamis that we want to focus on here are generated when there's displacement on the sea floor. And so in this little diagram that you can see, when we move the ocean floor either up or down, we displace water, and that volume of water is usually fairly large because these happen usually where we have a convergent plate boundary where there's subduction. And so there's a deep trench there at the subduction zone, so there's a lot of water to move. And so this huge volume of water then is displaced and moves out in all directions, and then of course can impact the coastline, and then of course we get damage from that. And so, like I said, we won't go into huge detail on tsunamis in this module because we'll focus a lot in the next module. But there are certainly some recent examples of large tsunamis that have impacted countries where there's been a big earthquake. And so this is just another illustration of how tsunamis are generated. One of the difficult things about tsunamis is in open water where they're formed, they're usually not very tall, so they're hard to see. But when they get closer to the coastline, and the water shallows, the height of the wave tends to grow. And so they can be pretty fast in open ocean. They slow down when they get to the coastline. And then they, of course, rise up fairly tall. And then they can cause some damage, of course. And so the idea that the wave is being squished or compressed is one of the reasons that it grows taller as it gets close to the coastline. And then, of course, these big waves can push in, and not just like a surfer wave crash, but they can push in miles and cause lots of damage, of course. And so that's another hazard that we want to be aware of when we talk about earthquakes and the impact, of course, to coastal communities. Obviously, if you have an earthquake that's not under the ocean basin, this isn't a factor. Or if you're far from the coastline, this isn't a factor. But there's, some other examples like, these trees here were sheared off by a large tsunami wave that impacted the coastline here. So there's definitely some power here. And there's a couple of examples, and we'll go into these in more detail when we talk about tsunamis in the next module. But there was a 2004 earthquake in Indonesia where there was a very large tsunami. And in 2011, there was another large tsunami, and both of these were results of large earthquakes that happened at convergent plate boundaries where there is subduction. And of course, these fault plains, these kind of plate boundaries, were near coasts, and these, people that lived here were impacted by that for sure. Okay, more, you say? Yes, there's more. So we also have this other thing to think about, which are landslides. And, if you think about it, you're probably, okay, that makes sense because the ground is shaking. And so if you have any topography, and look, if you're near a major fault zone and you're getting this compressional forces, you probably have some topography. Mountains are being created by this compressional force, right? We're uplifting areas. And so we get mountains and we have high areas. And so as we shake the ground, we can cause these steep slopes to fail. Material then moves down slope, and then of course that causes damage to structures or anything that's in its way. And so another example of that we can look into, and this is, once again, we can talk about this a little more. If you go to the link, you can see more information. But in Nepal, so this is where two continents are colliding. So we're not near a coastline here, and we don't really have subduction, but we still have a compressional force that's causing a large earthquake to occur. But here, this is where the Himalayas are. Why? Because we have two big continents smashing into each other. They're crumpling, they're uplifting big, tall mountains here. So very steep slopes in a lot of places here. Those fail. And of course, in this example here, lots of landslides occurred. So this was a huge factor because of its location and the type of faulting and the type of kind of boundary that we just discussed, these two continents crashing into each other. So certainly another hazard to be aware of when we talk about earthquakes. Fires. So another issue we run into is because we have lots of services that are underneath the ground, right? So electrical, water lines, these are under the ground gas pipes. And so when we get these shaking or breaking of the ground, we can sever these gas lines. And then all we need is a spark of some kind, and then we start a fire. And so then the fires rage. If there's debris in the roadway, difficult to put out because you can't move your fire engines along the streets. And then in addition to that, water lines also fail. And so then it's difficult to hook up to some type of system like a fire hydrant. There might not be any water. And so this is more of a secondary effect, but certainly something that, the 1906 earthquake was famous for this. A lot of the damage was related to the fire that occurred after the ground shaking. And so, it's definitely a destructive effect and something that we want to consider when we're looking at, earthquakes. So all these reasons we want to address these kind of issues is how do we combat those? Like, what can we do to prepare for a tsunami? What can we do to prepare for landslides or fires or things like that, right? Okay, another thing that we see that occurs, and I talked about this briefly, is this idea that as the energy waves move through materials, different materials behave differently. And so when you have hard bedrock, so this is a rock, right? It is turned into a rock. It can be a sedimentary rock. It can be an igneous rock. It can be a metamorphic rock. Those generally don't shake as much because they're bound together very tightly and the energy can move through fairly quickly. Now, certainly some rocks are better than others, but overall, we would argue that the bedrock is better than loose material. And the small loose material, like the mud-sized particles, the tiny pieces, are worse. Sand and gravel aren't very good either, but when we get the muds, those tend to amplify the energy much more than other materials. And the downside to that, of course, is near a coastline, this is where we get these big convergent plate boundaries that we have subduction. And of course, near coast, this is where the smaller particles are. And so they build up and they become land and we build on them. And then, of course, when there's earthquakes, those are the areas that fail more often. They liquefy easier, they shake more violently. And so this is where we get into trouble. And why we should also be aware of the geology, right? Where are you building your structures and what accommodations do you need to make because you have different types of material that you're building on, right? And so here's another example, same thing, but it's showing, yes, the igneous rocks are probably the best. Sedimentary rocks, okay, they're still good, but not. And then alluvium is just a general term for these large fragments, pieces, right? We're still here, we're talking not of rock, but of loose material. And once again, the small, tiny pieces, worst. Those are the worst types, and so we want to be aware of those things. And so what we also see is that there's sometimes this thing called resonance frequency. What the heck is that? Well, what happens is that the wavelength of the waves, the energy waves that are moving through the rock can vary. So how fast does the ground shake? Kind of really fast or really slow? And it can impact certain building heights. And so we know that in cities, we obviously have a range of building heights. In some cases, an earthquake will occur and certain building heights will have the more damage than like the really tall ones or the really short ones. And why is that? Well, it's the way that the energy is moving through the ground. And if it matches some of the what we call resonance frequency of these tall buildings, then you can get more damage just in those and not in others. I know it sounds a little weird, but this is an example here where there was an earthquake in Mexico City. Now, Mexico City is built on these ancient lake sediments. So when we think about lake sediments, it's a very quiet, low energy environment. Small pieces here. These are muds, silts, the stuff that shakes the most. And so when there was an earthquake here, there was a lot of damage. And of course, one thing that was noticed was these buildings in the 6 to 16 story range had the most damage. And so it seemed not odd, but something to like, why is that? Why would that be? Well, one of the reasons is that the wavelength of the energy waves that move through kind of matched the energy of the resonance of the buildings that kind of, I'm moving back and forth. I'm trying to grab a video here for you. All right, so here's another one we're going to look at. So this is showing that as you shake the ground here, so there's two things that you're looking at here. These little balls on springs, and they're comparing it to building heights. And so what you'll see is they'll shake this either fast or slow. And so fast means short wavelengths, right? So they're really short and they come very fast. And if they move it slow, that's long wavelengths. And you can kind of see that up here. And so what they're trying to illustrate here is that in this kind of range of wavelength, this height building shakes the most. And look at these others. They're not shaking very much at this kind of middle of the road. But if I shake it much faster where I have a short wavelength, look at this one shaking like crazy. And so the wavelength is short, I impact these smaller buildings more than these guys. If it's kind of in the middle, I impact the middle kind of height ones. And if I have these very long wavelengths where you're not shaking it very fast, what you'll notice is the large buildings, and in this case, the example is this blue ball here that's bouncing back and forth. You can see that the long wavelengths impact the really tall buildings, and they sustain more damage. So the argument for the Mexico City one was that it kind of had a medium wavelength, and it caused buildings in this certain kind of height to shake more than all the others, and this is why they had this issue with those height buildings failing or having the most issues, right? Okay, so that's that. All right, I'm trying to navigate my 16 windows I have open here. All right, what else I got for you? Okay, so the last couple things we want to talk about is prevention. What can we do to kind of save lives and reduce damage to our structures? And then can we predict? And so, of course, one of the best ways that we can prevent some damage is to determine where earthquakes occur and who's at the highest risk. And so making hazard maps is a huge way to do that, just like we do for volcanoes. Like, where are the hazards? If you live here, is ash going to fall on your house? If you live over here, is a lahar going to come wash your home away? We can do that for earthquakes here. So we can do it for where are the faults, where are the materials, and how might they behave during an earthquake. We can look at liquefaction hazards, right? Who's going to have some issues with this possible water kind of rising to the surface and liquefying the soil? We can make maps like that. We can just be like, okay, where do earthquakes occur? Because we know something about geology, we could say, hey, these areas are at higher risk than others because they're either near a boundary or there's old fault systems here or something like that. So creating these hazard maps is definitely a way to start to figure out how to reduce some issues, right, that come up when earthquakes occur. The other big thing is, of course, education. So how well prepared are you? What does the public know about an earthquake? Where to go? What to do? How might your home or structure behave during an earthquake? Do you have supplies set aside? Do you have a plan? Education here is huge. So we want to tell people, hey, you live in an earthquake-prone area, and if there is one, these are the things we want you to do to help minimize damage to your home or to anything around you, or of course to keep you alive. We want you to try to do these things. So having a plan, educating the public, huge. The other thing that we can do is building materials. And of course, we know that in high earthquake areas, there are different building codes that are required. And so in California, right, buildings are built differently. So we use the right materials. We use some, extra types of bracing and things like that to keep the buildings from shaking. Sometimes there's even some what are called isolators, base isolators, or shock absorbers, or there's weights up top. So all these ways to kind of keep buildings from shaking and to allow them to, if they do shake, they don't break or fall down, using rebar and concrete together, so you get some strength with some flexibility. And so some other things to consider when we're building buildings, right? How tall it is and weight and what we're using and all this kind of. So all these things are something we can take into account because we know, of course, what kills people, it's the buildings. And so we want to do kind of, here's a list of things that we want to be aware of when we're building our buildings. So you can kind of look through these and just make sure that you're aware of some of the things we can do to make our buildings stronger and safer. Okay, and then the last thing we'll do is prediction. Can we predict earthquakes? We're going to say we really can't predict them in the sense that we can forecast them. We could say they will happen, and there's a probability that a certain size earthquake would occur in a certain period of time. Like in the next 10 years, there's a 62% chance that a magnitude 7 or greater will happen in this area. That's about the best we can do. So we can't really say, yes, there's going to be an earthquake on Thursday at 5:25 a.m. and it should be about a 6.2. So put that in your schedule and prepare. So that's never going to happen. But there are a few things we can do in the short term and then potentially in the long term. And so in the short term, there's a few things, and I'll just list them here really fast. So, these things sometimes are helpful, sometimes not so much, but occasionally there are small earthquakes that lead up to a large earthquake. So, okay, not the best kind of prediction method, but if there's a small ground shaking, you should be prepared that there could be a larger one coming, and so you might want to get to a secure area. There are some other things that we can see. Sometimes we have sensors on the ground. We can see that the ground is uplifting or deforming. And remember, when we have an earthquake, we get this deformation because of the stress. So the ground does shift. Sometimes it can increase, and that would be a potential indicator that a failure is coming. We get water level drops in wells, and that's because the ground is cracking and allowing water to move easier through the rocks at depth, and that could change, levels of water in wells. There has been some anecdotal evidence of strange animal behavior. That hasn't really been scientifically proven, but, there's been horses run out of barns and dogs howling and some other things that may occur before an earthquake. And of course, this increase in radon gas emissions, you have to be monitoring for this stuff. This is something that would occur as the rocks crack and fracture and release some of that, but they're not these absolute, like, oh, this is going to happen. Because a foreshock, it could just be a small earthquake and be done. So difficult for the short term. For the long term, what we end up doing is we're trying to predict based on evidence that we have about what's happened in the past. And so one way is to find a fault and look for an area where you could trench along the fault and find layers that have been offset. In this example, you not only need offset layers, but you need some material that you can get a date on, that we could radiometrically age date. And if that's true, we could see how often the fault has moved, and then we could make an average and say, hey, according to the history of this fault and the motion on it, it looks like there's an earthquake every 50 years. And so there hasn't been one for 53 years. In the next couple of years, the chances of an earthquake are pretty high. That's kind of the prediction accuracy that we can do. Or sometimes we see that there's a gap. What does that mean? Well, that means that there hasn't been an earthquake in an area that I know is under stress. And so if there hasn't been one in a long period of time, that means that stress hasn't been released. Now, if there's an earthquake over here, 10 miles to the east and 50 miles to the west, but right in the middle, nothing, there's potential that stress needs to be released at some point. And the next place I would see the earthquake is in that gap zone where there hasn't been one. Because to the east, there's been an earthquake and it released the stress along that fault. And to the west, there's been an earthquake and it has released the stress along that fault. But in the middle here, it hasn't been released, which means that's where I would predict my next earthquake occurring, because the stress is there and hasn't been released yet, right? Sometimes we can monitor the stresses building up on the rocks, and if we see a spike in this increase in stress, that could be an indicator that that area might fail soon. And so this whole idea of a seismic gap here is the way that this fault here you see in this diagram, and it's showing kind of stress in different colors. And what happened here was there was earthquakes that kind of ran along this fault. As there was an earthquake, there was a release in stress, and then the next earthquake happened where the stress wasn't released. And then we had an earthquake and we released the stress, and then here's this high stress area, and that's where the next earthquake occurred. So it's this idea of looking where earthquakes haven't occurred, which doesn't seem, kind of intuitive, But of course, we're looking along a fault where we know stress is being applied here. We know there's stress here. So there's going to be an earthquake. But where's the next one? It's where there hasn't been one in a while because that stress is still hanging in there, waiting to be released. And so sometimes that's where we would predict the next earthquake occurring. And then the last thing I'll mention here is something called shake alert. And it's kind of, I don't know if we could call it a prediction, but it is a tool that would help you in an earthquake. And that is because technology, and we know something about how earthquake energy waves move. So if you remember from the previous module, we argued P waves, S waves, surface waves. Typically, the surface waves and the S waves do the most damage because they move through slower, and that can cause some issues. What we see is that because the P wave is so much faster, when an earthquake occurs, we have these waves that are moving out from the epicenter here, and we have a sensor that can detect the P wave. So just like it showed up on my seismograph first, as soon as it does, I can send a signal and say, hey, I detected this. In the next, 15, 20 seconds, the ground could start shaking. And so I could send that to a phone because the technology is fast. Electrons move faster than P and S waves. And so I can send out a warning that would say the ground is going to start shaking in 15, 20 seconds. Is that, a lot? Well, it could be. Because if you're in a building where the roof is going to collapse on your head and you can get out of that building in 15, 20 seconds, that could be helpful. If you could crawl under a desk to protect yourself from falling debris before the ground starts, that could be helpful. And so this doesn't work everywhere, of course. If you're super close to the epicenter, the P and S wave lag time is too small and you can't get a warning out. But there is a sweet spot where an area would still be impacted by the shaking of the ground causing damage, but you're far enough away where there's a separation in the P and S waves that I can record the P wave, give you a warning, have you do something to protect yourself before, all craziness happens and you get, some ground shaking. Okay, the only other thing I will mention is that on the main page, there's another clip from, I think it's the 2011 Japan earthquake that has some video of, people filming during the earthquake, which is kind of interesting to see. If you've never been in an earthquake, it gives you, I guess, a little experience. So you can go ahead and take a look at that to help you kind of understand what it might be like if you've never experienced an earthquake. Okay, so I think that's all I got for you for this one. It's probably a lot. And if you have any questions or you're confused about some of the content in here, please don't hesitate to get in touch with me.